Right, so next let's discuss convergence of martingales and submartingales. Right, so we will prove the following theorem. Now in this theorem we'll consider a submartingale xn(bn), which will be indexed by n between -infinity and +infinity. Okay, we'll choose this interval, or we'll choose the index to be between -infinity and +infinity in order to accommodate the example of reverse submartingale when n goes to -infinity. Okay, so this is a submartingale. Okay, and then in this setting we'll prove the following three statements. So the first statement will be that the limit in the reverse direction n goes to -infinity always exists. Okay, so we'll prove here that the limit x will denote that x minus infinity when n goes to -infinity exists almost surely, and the expectation of its positive part is finite. Moreover, we'll also show that you can include the index -infinity and this will still be a submartingale. So we'll show that xn(bn), including this limit, is a submartingale where b minus infinity is just a sigma algebra given by the intersection over all n of these sigma algebras Bn. So they are decreasing in the negative direction, and you'll just take the limit by taking their intersection. And we know that intersection of sigma algebras is a sigma algebra. Now in the positive direction, we'll need some assumptions. So here the statement number one was without any assumptions, but when you take limit n goes to +infinity, we'll assume that the expectations of xn are all bounded, or more precisely, for submartingales, the expectations of their positive parts are uniformly bounded. Okay, and the conclusion then will be that the limit in the positive direction also exists almost surely, and the expectation of the positive part of this limit will also be finite. The last statement will be the analog of this statement in part 1 about including the limit into your submartingale sequence, but for that we'll need a stronger assumption in the positive direction. So here we'll need that the whole sequence is uniformly integrable, not that just expectations are uniformly bounded. So in part 3, if your sequence xn, positive parts of the sequence, is uniformly integrable, okay, then you can include this +infinity into as an index in your submartingale. So then xn(bn) for all n between -infinity and +infinity is a right closed submartingale. Okay, and we already discussed in the first section that for the martingales, if it's a right closed, you must have uniform integrability. So this condition here is necessary for this statement. And of course here I should mention that the sigma algebra, so what is the sigma algebra b +infinity? It's just a sigma algebra generated by the union of sigma algebras over all n. So in the case when your sequence xn (bn) is a martingale, of course, martingale is also a submartingale, so all the statements about the existence of the limit above are exactly the same under the same assumptions. But in the last statement, of course, two inequalities will not give you inequality. So if you want to say that the limit when n goes to plus infinity can be included to close your martingale, well, essentially the proof that we are going to give for sub-martingales, exactly the same proof will give you equality for the martingale. So here I'll just state this, that the analog of part 3 will be that if xn is uniformly integrable, okay, then the sequence xn bn, where you include index plus infinity, will be a right closed martingale. Okay, so the proof that we'll give now for sub-martingales, it's just will immediately give this statement also for the martingale. Now, before I give a proof, let's consider one example of application for the reverse martingale. So actually, the proof of part 1 and part 2 and 3 will be very similar. So I will only consider the limit in the positive direction, so only part 2 and 3. So for part 1 of reverse martingale, let's consider an example which will be a new proof of the strong law of large numbers. Okay, so here we consider an IID sequence, and let's suppose that they are centered, so we don't need to subtract the expectation. And then if you recall, one of the examples of martingales that we gave was this reverse martingale, okay, where we considered the average Sn over n with the clever choice of the sigma algebras. So B minus n was a sigma algebra generated by the sum starting from n, or Sn and the sequence xn plus 1 and so on starting from n. And the index here was minus n less than minus 1. So the negative integers going to minus infinity. So in this case, by the above theorem, or by part 1 of the above theorem, we know that the limit exists almost surely. So there are no assumptions there except the existence of expectations. So the limit, let's denote this again, x minus infinity, exists almost surely. And moreover, it's b minus infinity measurable, right? Where we recall that b minus infinity was just intersection over all n of the sigma algebras Bn. So this limit is measurable on this intersection of the sigma algebras. And in the strong law of large numbers, we want the limit to be a constant. So what we have to notice here is that this limiting sigma algebra is essentially a trivial sigma algebra. So something is measurable on the sigma algebra must be a constant almost surely on our probability space, right? And for that, we notice that any events in the sigma algebra, so if you consider an event A in the sigma algebra, it must be symmetric. Okay, in a sense that it is not affected by the permutation of finitely many random variables x, right? And of course, the reason for that is that for a sigma algebra b minus n, it depends on x's only on the first n x's only through the sum. So the permutation would not affect a measurable event here. And we take intersection over n, so that means that statement should be true for all n. So in particular, we can apply Hewitt-Savage 0-1 law. Okay, so by Hewitt-Savage 0-1 law, the probability of such event must be either 0 or 1. Okay, And so as a result, this is essentially a trivial sigma algebra, so the limit, which is measurable, must be a constant almost surely, and in particular because this is a martingale, the expectation of this limit must be the expectation of the first element in the sequence, so that was just x1. Okay, and because x minus infinity is equal to its expectation, almost surely we get a new proof using martingale convergence of the strong law of large numbers. Okay, so now let's look at the proof of part 2 and part 3 of this martingale convergence theorem, and let's start with the proof of part 2. And again, we already explained as a motivation that we will look at any pair of rational numbers a less than b, right? And we want to count this number of upcrossings of this interval ab up to time n. And so what we want to show in order to prove the convergence is that the limit of this cannot be plus infinity with positive probability, or in other words, right, this number of course is increasing when n goes to infinity. So this limit exists, but it can be infinity only with probability 0. And then our discussion before means that you cannot oscillate between a and b infinitely many times, so you must have a limit. And in order to conclude that this probability is 0, we only need to apply this Doob's upcrossing inequality. Okay, which tells us that b minus a times the expected number of upcrossings is bounded by this expectation of xn minus a, the positive part. But then, of course, we can just bound this by absolute value of a plus the expectation of the positive part of x. And here is where our assumption comes in. The assumption was that these expectations are uniformly bounded. So this is bounded by some finite constant for all n. And then when you let n go to infinity, now you just apply, monotone convergence theorem to conclude that the expectation of the limit when n goes to infinity of this number of upcrossings, right, it will also be bounded by the same constant, so it will be finite, and as a result this limit must be finite with probability 1. So that implies that this x plus infinity, the limit of our sequence xn, exists almost surely. Okay, so that concludes part 2. And yes, we had one more statement in part 2 that the expectation of the positive part of the limit is finite, but this is just by Fatou's lemma, right, which says that expectation of the lim_inf, which in this case is the limit, is less than or equal than lim_inf of the expectations, which are all bounded by some constant. And so this finishes part 2. Okay, now to prove part 3, well, first of all, so we want to include this limit and use it to close our submartingale. So first of all, of course, we notice that this limit is measurable with respect to the sigma algebra b plus infinity, which we defined as a sigma algebra generated by the union of the sigma algebras. Okay, it's measurable because xn is measurable on Bn, so xn is measurable on the sigma algebra, so the limit is also measurable. And in order to close our submartingale, right, what we need to show is the statement about conditional expectations, or let me write it more explicitly in terms of the definition of conditional expectation. So if we take an event in some sigma algebra Bm, so here we fix some index m. Then we want to show that the expectation of xm on this event is less than or equal than the expectation of this limit on this event, right? And that shows that you can close, once you include x plus infinity into our sequence, you still have this inequality for conditional expectations. Okay, so that's what we want to show here. And how do we show this? Well, our assumption was that the positive parts of our sequence form a uniformly integrable sequence. And instead of truncating at 0, just taking a positive part, what we are going to do is just truncate at any constant a. So we'll notice that, of course, if you take a maximum between your sequence and a for some real number a, this will still be uniformly integrable. Okay, because, it only differs from the positive part by a constant. Now, moreover, as we have seen already several times, this type of truncation of a submartingale still is a submartingale. So for any m and n, you have this comparison of conditional expectations, or you can write that the expectation of this truncation at time m on the indicator of that event is controlled from above by the same expectation at time n. And then we use the fact that we already have the convergence, so we know that this converges to this limit almost surely. So we have this almost sure convergence, plus we have uniform integrability. And this was one of the technical results that we proved in the first section, that convergence in probability plus uniform integrability implies L1 convergence. So in particular, the expectations converge to this expectation here, and you have also comparison between the expectations in this direction. So in other words, this shows that expectation of this truncation at time m is controlled from above by the expectation of this truncation at time infinity on this indicator. Okay, and then we just let a go to minus infinity and apply monotone convergence theorem to conclude the same inequality without the truncation. And that's exactly what we wanted. So this proves part 3, and so it finishes the proof of this theorem about convergence of submartingales. Okay, and notice that for martingales, the same argument that we gave here at the end without any truncation, under the assumption that the martingale itself is uniformly integrable, would give us that you can close the martingale and get a right closed martingale, okay, just like I mentioned above. For martingales, okay, what this shows is that uniform integrability is equivalent to being right closable, right? When your index goes to plus infinity, right closable must be uniformly integrable, and now we showed in the opposite direction. And remember, right closable means that your whole sequence is just generated as conditional expectation of some integrable random variable given some sequence, increasing sequence of sigma algebras on your probability space. Okay. Now the next result we are going to state is some sort of characterization of the limit of this sequence in terms of the random variable x and the sequence of sigma algebras. And this is called Levi's convergence theorem. Okay, what this theorem says in the above setting is that when you take the limit when n goes to infinity of these conditional expectations of x given Bn, you are just going to get the conditional expectation of x given the sigma algebra B plus infinity, which we considered above. It's just a sigma algebra generated by the union of sigma algebras Bn. And the proof of this result is pretty straightforward, kind of very similar to what we just did above. So I'm going to leave it to the notes, but let me just make maybe one comment here is that, of course, in the case where your refinement of sigma algebras Bn in the limit gives some sigma algebra where your random variable x is already measurable, then of course it tells you that the limit is equal to x. So if x is b plus infinity measurable, then this limit x plus infinity that you get in this theorem is just x itself, right? So, you know, if you think about the example of this cat martingale that I considered in the first section, when we chopped the squares into 4 pieces at every step, of course you can easily check that in the limit the sigma algebra that you will get will be the Borel sigma algebra on the square. So in that case, in the limit you get exactly the image that is used to generate your sequence. Okay. All right, so that's one quick comment, and let's just give one final example of application of this convergence theorem that we proved above, and this is the improvement of Kolmogorov's strong law of large numbers. Okay, in chapter 2 we proved the following result. So let me remind you what Kolmogorov's strong law of large numbers was. We considered independent random variables, and we considered some sequence of numbers Bn increasing, so it was monotone and going to plus infinity. Now the random variables were centered, and the assumption was that the sum over all n of the variance of xn or expectation xn squared divided by bn squared was finite. And the conclusion under all these assumptions was that when you consider the sum of your random variables, so Sn as usual is the sum of x1 xn, then Sn divided by Bn converges to 0 almost surely. Okay, and what we are going to do now is replace this assumption of independence by the following improvement, or by the following relaxed assumption, namely that the expectation of xn plus 1 conditionally on random variables up to time n is 0. Okay, it's the same assumption that we have used above in the second Kolmogorov's inequality. And how can we conclude with this strong law of large numbers under this assumption? Well, we consider the following martingale. So we consider yn to be the sum from 1 to n of xk divided by bk. Okay, and under this assumption here, this is clearly a martingale, right? Because if you take conditional expectation, just the future random variables will disappear. And so we want to conclude that this converges, and we are going to check uniform integrability of this sequence. So in other words, we want to show that expectation of absolute value of yn on the tail, on the indicator where this is greater or equal than m, is small uniformly over n for large m. And of course this actually just follows from the fact that the second moment of yn is bounded uniformly, because if you multiply and divide by this constant m, on this indicator you can replace m by yn and you will get inequality, right? It will just increase here, and we can also drop the indicator. And then when you square out the sum in the definition of yn, you'll just get sum from 1 to n, expectation of x k squared over b k squared, and the cross terms I and j will cancel here, right? So the expectation of xi xj for I not equal to j will be 0 exactly by this assumption here. And so recalling that our assumption in Kolmogorov's strong law of large numbers is that this whole series, so sum from k from 1 to infinity, is finite, right? We get an upper bound uniform for all n that goes to 0 when m goes to infinity. So indeed our sequence is uniformly integrable. So by the previous convergence theorem, this martingale yn converges almost surely. Okay, and then we conclude, just like in the proof of Kolmogorov's strong law of large numbers in chapter 2, we appeal to Kronecker's lemma. The convergence of almost sure convergence of the above series implies that Sn divided by Bn goes to 0 almost surely. Okay, and so we obtain the Kolmogorov strong law of large numbers under this very relaxed assumption. Instead of independence, you just need that your future random variables are on average 0 given the sequence up to time n. Now in exercises we give a similar improvement of Kolmogorov's 0-1 law, where the independence assumption on the random variables is also relaxed. But this example here, it wraps up this section 3, and so we finish here the chapter about martingales.